More on enthalpy. We have seen three main ways to calculate enthalpy. I can't write very fast. Our three main ways is what we spent the last couple of class periods on is calorimetry, where you do a reaction in a calorimeter. If a calorimeter absorbs heat, it's because a reaction lost heat. You calculate Q, and then you convert it to delta H using the moles of the reaction converted. Another way is from tables in the back of the book. Or entire books of all kinds of enthalpy values. And a third way, which is really sort of an offset of tables from the back of the book, is from an enthalpy plot, an enthalpy graph. So using those three main ways, we can calculate all kinds of enthalpy values. There are enthalpy of formation values that we have talked about, and we'll talk about some more. There are enthalpy of atom combination values that we have talked about, and we'll talk about some more. There are delta H of vaporization. That tells me the enthalpy required to vaporize some sort of liquid, so turning a liquid into a gas. There are enthalpy values for solvation. That means dissolving a solid in water and letting that thing dissociate and how much energy is absorbed or released in that process. There are enthalpies of, what else? How about enthalpies of bonds, like an OO double bond? I'm saying that because it's going to lead into what we are going to do in the next chapter, but there are lots of enthalpy values. That's all my brain has for me right now, but there are more values than that, more types of enthalpy values. What each reaction is measuring, if it's a delta H formation, what you're measuring is a certain thing. If it's an atom combination, what you're measuring is a different thing. If it's a vaporization, I already said that's liquid going to gas state. If it's a solvation, it's a solid becoming aqueous. Like the type of enthalpy that you are discussing tells you what kind of equation is associated with that enthalpy. What the heck do I really mean here? If I'm being asked for delta H of formation of methanol, when I am given a value, I probably should have looked up this value, but I didn't. When I am given a value, that value corresponds to a very specific equation. And formation enthalpies means combining elements in their standard state in the simplest ratio possible to make 1 mole of product. Oh, yeah, that was a lot. Carbon is normally a solid. If you look on the periodic table, the color-coded kinds, on the one behind me, it's written in black because it's a solid in its standard state. The periodic table tells me it's a solid in its standard state. I can combine that with 2 moles of hydrogen gas, and that's H2 as a diatomic, because hydrogen in its standard state is a diatomic, and oxygen in its standard state is a diatomic, and it's a gaseous diatomic. But I need half a mole of it because I only need 1 oxygen atom to get me CH3OH, liquid. I should have specified that liquid. This equation is an enthalpy of formation equation that's associated with that value. An enthalpy of vaporization of water, we'll say, that's our standard thing, but I could do the same exact kind of equation for methanol or ethanol or anything under the sun. A delta H of vaporization is water, liquid, becoming water gas. Nothing is changing about the species, like these are combining together to make that. Nothing is changing like as far as who's partnered up with whom. It's just the physical state is changing. And that bottom equation is associated with this delta H of vaporization value. We have already seen that enthalpies of atom combination What's defined as 0 in an atom combination enthalpy is atoms in their gaseous state, single atoms as a gas. It doesn't matter that H2 is stable as a diatomic. We're not worried about stability. We're combining single atoms as a gas. So if we combine something like, I realize that I didn't tell you what I'm combining here. How about C6H6, benzene? I didn't look up the values of any of these, but all I'm wanting to do right now is write an equation associated with the atom combination of C6H6. So C6H6 in its standard form is a liquid. I should have told you that up there. My bad. That's what happens when you're just making it up while you go. I'm combining single atoms in their gaseous state. So that's carbon as a gas plus hydrogen as a gas, combining together in the appropriate ratios to make 1 mole of product. So 6 of these and 6 of those makes benzene. This equation is the atom combination equation associated with that enthalpy value. Okay, so it doesn't matter what kind of system you choose, whether you use atom combination or formation enthalpy values. When you need to calculate an enthalpy of a reaction, consistency is what matters. So I can calculate delta H of this equation using my previous stuff, tables in the back of the book. I can calculate delta H of that vaporization by finding enthalpy of the products minus enthalpy of the reactants. I'm trying to find my pen. There we go. Delta H of the reaction is enthalpy of the products, so enthalpy of H2O gas, minus delta H of the reactants, so that's enthalpy of H2O liquid. It does not matter if these enthalpies are formation enthalpies or atom combination enthalpies. Because enthalpy is a state function, delta H of the reaction is going to be the same value regardless of which tables you use. It's just the way the value in the table was found is different depending on whether it's formation or atom combination. So if I looked up these actual values, I better get the same number regardless. You cannot and shall not cross systems, and what I mean by that is you cannot look up one atom combination enthalpy and one formation enthalpy and expect to get a right answer. Do not. Use formation only or atom combination only to work a single problem. Okay, maybe I have explained that well enough. I don't know. We'll see. So the textbook has formation values, enthalpy of formation values in the back. The chem activity book has atom combination values in the back. If we were to draw an enthalpy plot of this reaction, the 0 point for atom combination is atoms in their gaseous state. So all of the atoms that are involved in here, I've got 4 hydrogen atoms and 4 oxygen atoms. So 4 moles of hydrogen as a gas is defined as 0 in my chem activity book, and 4 moles of oxygen as a gas is defined as 0 in my chem activity book. The reactants have some enthalpy value that is lower than 0, some negative enthalpy value. Let's put them right there. The products, if I actually look up the values and sum them up, the products have an enthalpy value that's lower than the reactants. So because I know that I'm going to go through the transition reactants to atoms, atoms to products, I can put my up arrow over there and my down arrow over here, but the net transition is from reactants to products. It's exothermic. That change is all that I'm actually measuring, products to reactants. Are atoms in their gaseous state ever actually created when you turn liquid peroxide, liquid hydrogen peroxide into water and oxygen gas? No way. It's just this is my reference point that everything else is referenced against. So in the textbook, my reference point of 0 kilojoules is elements in their standard state. So I've got hydrogen on the reactant side, so H2 is the stable standard state of hydrogen, and O2 is the standard stable state of oxygen. So those values are what's defined as 0 for formation enthalpies. See, this is atom combination, this formation. I still have a shelf that has reactants on it. I still have a shelf that has products on it that's lower. It's still endothermic for me to go from this negative enthalpy value, and I know it's negative because I've looked it up in the back of the book. I go from this negative enthalpy value up to the elements and down to my products. The net transition is exactly the same. When this reaction actually happens, do I ever form elements in their standard state? No. But enthalpy is a state function. It doesn't matter how you get from this shelf to that shelf, the transition is the same. And my measured enthalpy on the atom combination tables, negative 196. It's an exothermic reaction that releases 196 kilojoules per mole. So is that one. Does not matter which reference table I use. Oh, are we going to get it? I hope we're going to get it. When I look at enthalpy plots, I can think about and calculate delta H of an enthalpy plot a couple of different ways. So if I'm going to see if I'm going to look at my enthalpy plot like this, where I've got reactants here down to products here, I can know, and I'm just making up numbers here, I can know that this is at negative 300 kilojoules. And because I want my math to be easy, let's put this one at negative 350 kilojoules on my y-axis. So I can do products minus reactants. Delta H of this reaction is negative 350. I'm telling you the enthalpy value on the y-axis minus negative 300, the enthalpy value on the y-axis for my reactants. So it's really plus a positive. Delta H of this reaction, Rxn, is negative 50 kilojoules overall. If I want to determine the enthalpy value from my enthalpy plot, and this, we said there are 3 ways you can determine enthalpy. Calorimetry, we've already done that. Products minus reactants, we're doing that now, and we've done that already a little bit as well. And finally, I can know that this transition that's pointed up requires 350, nope, not 350, my bad. I will edit this, but I'm not going to edit that out because I like you to know that I make boo-boos too. That requires an input of 300 kilojoules to get to this atom's state. That will then release 350 kilojoules. So if I'm given a plot, because my upwards arrow, I've already changed the sign to be positive, it's exactly the same as what I'm doing up here. That minus a negative is the same thing as plus a positive. So delta H of my reaction, when I'm given an enthalpy plot, I can simply sum together my 2 arrows because I've changed the sign already. I hope that this makes some of the things that I've seen you are confused on more clear. But I could have just made the hole deeper. Let's hope that I didn't. Okay, on to Hess's law. Hess's law says enthalpy is a state function. And it doesn't matter when you go from A to Z, whether you go A to B to C to D, all of a sudden magically to Z, or whether you go straight from A to Z, no stopping, no, do not pass go, do not collect $200. It doesn't matter how you get there. Enthalpy is a state function. The net change from A to Z is going to be the same regardless. So we use enthalpy, we use calorimetry to measure enthalpies of certain reactions, and then we take those very well-known certain reactions and compare other reactions that we cannot easily or directly measure to determine their delta H. Hess's law is also known as the indirect method, determining the enthalpy of a reaction that you cannot measure directly for one reason or another. So, let's say we cannot measure this reaction directly for one reason or another. We actually already know what it is because we saw it in the last slide or a couple of slides ago, but yeah, let's pretend we can't measure this directly. If I'm given these two equations and enthalpy values of these two equations, I can use these equations to determine the enthalpy of this reaction that I cannot measure directly. Enthalpy is a state function. We don't care what you go through. We care that you end up in the right position. So if I sum together those two equations, H2O2, H2O2, I got two of those. Those are both on the reactants side, and they do not cancel out with anything on the products side. H2O2 must stay in my equation. But I minus is on both sides of my equations. So if I were to sum these together, I minus on the product side, I minus on the reactant side, cancel that thing out. It's not a spectator in this case. It's called a catalyst, actually. But I minus cancels out because it's on both sides the same. IO minus. It's identical on both sides as well, so cancel that thing out. So I end up with only H2O2 as my reactant and H2O liquid, not one but two of them, and O2 as a gas as my summed product of these, product of these reactions. When I add together reactions, I also need to add their delta H's, because I can say delta H of this reaction is the combination of the delta H's of those other reactions. So 69.3 plus negative 265.4. I just paused it to do the math because I'm silly and my brain is dead. But it's 196.1 kilojoules per mole. I could have told you that exactly because it was my same example from a couple of slides ago. I can find the enthalpy through products minus reactants if I have all the enthalpy tables at my disposal. I can find the enthalpy through looking at an enthalpy plot and adding together the arrows and stuff like that. I can find the enthalpy through calorimetry questions like we've done all the day on Tuesday. Or I can find delta H from the indirect method, also known as Hess's law, where I'm given two equations that can be combined in some way to equal my desired equation up here, and I add together the delta H's as well. Whew. Let's do another one of these. Hess's law, I really like Hess's law. Students like Hess's law. It's good. There are worse things we will do, absolutely. So if I have these three equations at my disposal, and I want to calculate the standard enthalpy of formation of CS2 liquid, the first skill I need to have is write the enthalpy of formation for CS2 liquid. Oops. So the first half of this video was all about determining or writing equations associated with enthalpy values. The standard state of carbon is as a solid. The standard state of sulfur is as a solid. This equation that I'm giving here has more details than that. It says graphite and rhombic. The reason it says those things is if you look through a delta H of formation table, you will see carbon as a solid, which is called diamond, and you will see carbon as a solid, which is called graphite. Both of those are carbon as a solid, but one is more stable than the other. How do I know which one is the standard state? Well, it's the one that is equal to 0, the one that has an entry in the table that says carbon, solid, 0. That's the right one. That's the one that's the standard state. So that's how I know graphite is the 0 value. Okay. So there's my standard enthalpy of formation. So I need to combine these equations some way to equal this equation. Carbon graphite is a reactant in both of them. So I'm going to start by rewriting my first equation exactly as given, no changes necessary. Done. See graphite, exactly as it was in that first equation. S rhombic is a reactant in my desired equation, and it's a reactant up here. But this desired equation has a 2 out front. So I need to multiply this entire equation by 2 in order to get my eventual equation to add up to what I want it to be, to add up to my desired. So multiply the entire equation up there by 2, which also means multiply the delta H by 2. Whatever you do to the equation, do the exact same thing to the delta H. So that gets me this. And finally, there's my S rhombic in the right ratio. And finally, my CS2 liquid is a product. And in this equation, there it is as a reactant. So that means I need to reverse this whole equation, where CO2 and SO2 are reactants, and CS2 liquid is a product. When I reverse an equation, it means I change the sign on my delta H. Reverse an equation, reverse the sign of delta H. There's my reversed equation with my reversed sign, and my CS2 liquid is appropriate in the product spot. So then I'm finally ready to sum together these reactions. My hope, my plan, if everything works out magical, is everything cancels except C graphite plus 2S rhombic yielding CS2 liquid. So I got 1, 2, 3 O2s on the reactant side. 1, 2, 3. Cancel those with 1, 2, 3 O2s on the product side. I got a CO2 on the reactant side. I got a CO2 on the product side. Cancel that thing. All that's left is I got 2 SO2 and 2 SO2. Cancel that thing. What I'm left with is my desired equation. Whoop, whoop. And all I need to do now is sum up these delta H's. So negative 393.5 plus 2 times negative 296.1 plus 1072. And I get an enthalpy of this reaction is positive 86.3. Oh, I'm so tongue-tied. 86.3 kilojoules. Whew. Hess's law is not the worst thing. We will certainly do harder things. Be good at Hess's law. I got faith in you. Goodbye.